Good afternoon. I'm Brian Cantrell. I'm here with Dave Pacheco. We are from Joyent. So first of all, how many folks were at Surge last year? A lot of hands. That's awesome. How many thought that Theo's characterization of my keynote as interesting was a euphemism for a rodeo clown? Okay, thank you. I'm glad to know I'm not the only one that. Of course, Theo. Thank you. I thought that was what you intended. So one of the great things about Surge, I think, is that we learn about one another's failures. I love Ben coining disaster porn. I realize that I'm a disaster porn addict. I wish I weren't a disaster porn star as frequently as I am. That's what I want. I actually want to get out of the porn making industry and start getting into the porn watching industry. So this talk is going to be, I would characterize this as, Dave, I don't know if you agree, I think characterize this as a soft porn talk. This is like a Victoria's Secret for, this is the kind of thing you would read when you were 10 and get kind of excited about. This isn't something, I've seen some hardcore porn today. I don't know about you. I watched some serious kinky stuff, which is good. I can never get enough. But this is going to be soft porn. But I did want to give you a little teaser, because I think speaking for Joyent, the thing that was most valuable for us for last year's Surge is last year's Surge came at a time when we were really struggling with a production issue that we believed was due to Intel C-states. We believed that Intel C-states were like the octopus reaching up and strangling us. And Rod Cope's talk was incredibly valuable because Rod described the exact same problem on a completely different stack. And we knew then that our hypothesis was likely correct. And so for me, that kind of naming and shaming is extremely valuable for Surge in terms of learning these failures. Now, you should know that, by the way, that for Rod in particular, this particular failure drove him out of his mind. It actually drove him insane. Because based on his lightning talk last night, he believes that God intended CoffeeScript. So these failures can exact a heavy, heavy psychological toll. But for us, I don't know, who stands up their own hardware? Oh, God, that's not enough hands going up. This is supposed to, all right, wow, OK, that's great. I mean, everyone's on the cloud, so that's terrific. I don't know if you have anyone having Dell perk issues? OK, so we're seeing a rash of ECC errors, fatal ECC errors on the perk DIMMs that we're being told, no, it's just you. Baby, it ain't just me. We're seeing way too many of them. So if you're seeing any Dell, yeah, let's talk. Yeah, OK, yeah, OK, wow. Good. I knew this would happen. Thank you, Surge. I love you, Surge. Thank you. Yes, let's talk. OK, we have a lot to talk about. Dell, you're going to be sorry. Dell is going to try to shut down Surge next year. The hardware vendors are going to be like, no Surge. OK, that's actually not what we're here to talk about. But I do want to talk about Surge from last year. Not my talk on everything that can go wrong. But rather I had a keynote last year, the interesting keynote, on data-intensive real-time, the emergence of these data-intensive real-time systems, web-facing systems that were suddenly having the properties of real-time systems. And I dubbed these dirty systems. I'm not sure if the term is caught on or not, but we like to say it anyway. And we discussed some of the ramifications of these dirty systems, of these data-intensive real-time systems. And a big one for us was the need to observe latency in production. That when a real-time system is different from a normal system because the correctness of the system is its latency. If the system is late, it's wrong. If the data is late, it's wrong. And when you're building those kinds of systems, you need to be able to see the latency because you need to be able to assess the correctness. And I called this out as a really big problem and a problem that we at Joyent saw. But of course, I was really just yakking on about the problem. I hadn't actually started anything yet. Of course, I'd only been at Joyent for about 30 days at the time. But after Surge 2010, we got to work on this. Dave joined the team. And we started working on a facility to do exactly this, which we call Cloud Analytics. Cloud Analytics was first stood up in production at Joyent in March. We then shipped it out as a product in April. And we have continued to improve it since then. So we've done a lot of work on Cloud Analytics. And we don't want to just describe Cloud Analytics to you, although we certainly think it's interesting. What is interesting to us about Cloud Analytics, we think it'll be interesting to a broader cross-section of folks, is it is itself a dirty app. So Cloud Analytics is itself a data-intensive real-time app. And indeed, maybe one of the early Node-based dirty apps to be deployed into production. And as a result, we think that our design decisions may be helpful. And we're going to talk about, and again, this is where we get into the soft porn. We're going to do some disaster soft porn and talk about the decisions that we made. And we've gone back and kind of revisited all the decisions we made over the last year, and the ones that made sense and the ones that didn't make sense, and the ones that crept up on us in production. and then the ones that haven't crept up on us in production yet. So we'll talk about all of those. First, I just want to get kind of the objective that we were trying to achieve with cloud analytics. And then Dave's going to take over, and he's going to walk you through the architecture, some of the design choices, and then we'll actually wade into our production experiences. And we will try not to throw too many technologies under the bus in the process, but we probably won't succeed. Let's talk about the design objective of cloud analytics. We really wanted to focus on the source of the pain, which is latency. And I think you've seen this in other talks. If you were at Artur's talk this morning, first of all, if you're playing the Artur Bergman drinking game, where you have to drink every time he says fuck, you have to tell someone else to drink every time he says SSD, you didn't get actually as drunk as I thought you would. That was kind of surprising. I was really waiting to get hammered, but it didn't quite happen. But if you were at Artur's talk, he talked about the importance of not just measuring operations, but actually trying to measure latency. Well, latency is very hard to measure, but it is the essential thing. You can't just look at the number of operations per second that something is doing, because if the number of operations per second drops, that could be because there is less work to do. That's happy. And it could be because the work you're doing is taking much, much longer. That's very sad. You need to differentiate those two, and you need to do that by measuring latency. For us, and the problem that we saw at Joyent as a cloud company, is that as you are deploying your apps into a cloud, or if you are an operator standing up a cloud, you need to see that latency across many, many, many machines. If you're deployed on Amazon, how many times have you wanted to see your latency across your entire fleet? So you can actually see, where do I have a latency problem beginning to bubble up before it becomes critical? That's hard to be able to do that. I mean, you don't want to just have a bunch of graphs exploding off of the page. And this has to be across, obviously, it's a distributed system, and we need to do it in real time. We feel it's very important to be able to do this in real time. So could we visualize latency as a scalar? So that is to say, take a value and graph it. Well, you can do this, and you can visualize latency as an average or what have you, but you're hiding a lot of outliers here. And in a real-time system, it is the outliers you care about. You don't care about the happy state. What you care about is those outliers, because those outliers, one, are subpar service. Secondly, they could be an indicator that something is beginning to fail. You really want to see those outliers. Now, you can use percentiles. That's better, and Artur described that in his talk. But percentiles still is not good enough. You're still missing critical detail, and it's hard to gather that information. So latency as a scalar is kind of a non-starter. And we really struggled with this problem, by the way, in a previous life, when Dave and I worked together on the Fishworks team at Sun. We struggled with how do we visualize latency. And it was our colleague Brendan Gregg who had the breakthrough. After really years of kind of struggling with this problem, Brendan had the insight of, actually, let's visualize latency not as a scalar, but as a heat map. And what we're going to do is put time on the x-axis, put latency on the y-axis, and then use color saturation to indicate the frequency of an event at that particular time, at that particular latency. And so we did that, and we did that again in a previous life and in a previous product. We did this, and boy, it was really valuable. And all of a sudden, we saw things that you could never see before. But in many ways, it was really a big tease, because what you would do is you would see something like this. And this particular example is taken from MySQL query latency. This is MySQL query latency over, obviously, a period of time. And you see what are obviously patterns in there. And you immediately have follow-up questions. And you want to ask questions of that data. The problem is, this is the end of the dimensionality of the data. There's no more data there. So I can't, if I want to have a question, for example, if I want to know what table is this, if I want to know what machine is this, if I want to know all these different ways of looking at this latency, at a guess. You only have this one additional level of dimensionality. At Joyent, we appreciated that was a huge problem, because we would see all of these patterns that were crazy, but we couldn't explain them because we couldn't get that additional level of dimensionality. So what we actually explored, and then went and implemented, is what we call a four-dimensional heat map, where we, again, still use x-axis as time, y-axis as latency, color saturation as count, but then we use hue to denote an additional dimension. In this particular case, this is the database table. But as you can imagine, and this is kind of the canonical example that I was thinking of as we were thinking of this, is I'm looking at I/O latency across all of my machines. I want to see that collected together in a heat map, but the additional dimensionality that I want is by machine. So if I see a latency outlier here, if I see a latency outlier there and I want to know where it's coming from, I can click on it and see the banding. And I can see, for example, are all my latency outliers coming from one machine? Bad disk, I mean, sky's the limit, could be a lot of things. Or is it coming from a smattering of machines, in which case maybe I'm simply at head latency or at rotational latency. So this is what we wanted to go build. And the challenge was, how do you go build this to be completely real time? To be able to do this across a distributed system and in real time. And we're hoping, by the way, that Dave is now going to take us kind of through the architecture here. And by the end, I think we're going to hold questions to the end, and we'll demo the facility in production, so you get a chance to actually see what it looks like. But for now, Dave, you want to take it away and with an architectural overview of what we were actually building.
Yeah, so Brian just described where we're going. We're trying to build this thing that is able to show us in real time heat maps describing latency of software deployed across the cloud. And so now I'm going to talk about the different components in that system, then we'll talk about the design decisions, and then the issues that we've had with that, and also the places where those have worked out pretty well. So we have basically three main architectural components that we're going to be talking about. The first is the configuration service. This is the external endpoint to what's called the Cloud Analytics Service. That's the umbrella for this whole thing. That manages configuration, and it handles all requests from the outside. We have an instrumenter. This is the component that lives on each physical server in the cloud, which is hosting customer instances. We call those compute nodes. And gathering data, performance data from that node and sending it to one of several aggregators. The aggregators are actually combining this data from multiple different instrumenters and serving requests for that data that are proxied via the configuration service to a client. That was a lot, so let's look at a diagram. Here we have a bunch of compute nodes. Remember, these are hosting customer instances on the right-hand side. We have over here, we call it the data center head node on the left. That could be anywhere. That just happens to be where we put it. We have one configuration service there and a bunch of aggregators. What happens is a client first makes a request via our HTTP API and says, I'm interested in like node HTTP requests decomposed by latency and remote IP address. The configuration service first picks an aggregator that's going to be responsible for maintaining this data and serving those requests, communicates via Amqp to that aggregator, and then also talks to all of the instrumenters in the cloud responsible for that customer's instances, and says, start gathering this data for HTTP requests, decomposed by latency and remote IP. Those compute nodes start gathering that data, and they report it once per second to the aggregator that was picked for this instrumentation. We call this whole thing is an instrumentation, this request to understand node HTTP operations. And then sometime later, this is like a second later, the client makes another HTTP request to actually get that data, get the data for the last second. And it just does this every second and draws the graph. We'll talk a little bit more about how it draws the graphs and the heat maps. We'll talk about that a little bit later. Here's an exploded view of the instrumenter, just to give you a sense of what it looks like. All of the components in this distributed system are written in Node.js. So the config service is a Node.js service. The aggregator is a Node.js service. They're talking to the instrumenter, which is a Node.js service, running on the compute node.
Dave, is there any problem that can't be solved with Node.js?
We'll get to that.
OK.
So we have the instrumenters on each compute node. The compute node is running some number of customer instances. These may be virtual machines using KVM, in which case it's an actual operating system kernel running in there. Or it might be a virtual OS instance, in which case it's an instance of our SmartOS operating system. But regardless of what type of instance it is, there's one kernel running underneath all of this, which is essentially our hypervisor. And dtrace is the dynamic tracing facility that we use to gather most of the interesting data. And the important bit here is that because dtrace is living in the kernel, essentially, of the hypervisor, it's able to see data from all of the customer instances. We don't have to have an agent inside each customer instance. We just have this one kernel facility which is able to see all of them. The instrumenter it has pluggable backends, of which the dtrace one is simply the most interesting. That's why we're talking about it. It communicates via libdtrace to the kernel using a node module called node libdtrace. And that's kind of the overview of the instrumenter and how that plays together. So now we're going to talk about some of the design choices. First of all, who here has never seen the Node Hello World program before? OK, great, perfect. So the two important bits here are it's so little code because HTTP is such a first-class API in Node, and that this simple server in one thread is able to be highly scalable because of the asynchronous model.
So who here has written Node? Written Node? Deployed Node into production? OK, pretty good. Cool. That's good.
And the key ideas for us are, the reason we're so excited about Node for building these systems are, first of all, JavaScript already has the rich support for asynchrony because of its history in the browser. We gain from the competition among various high-performance VMs. Node uses the V8 VM, which is used in Chrome, which competes with Firefox and IE. So we gain from all those that performance competition. And the Node API, you may not have actually noticed this, but it's actually the same system abstractions that Unix provides. It's basically, so we're using the same abstractions we've used for systems programming for many years, and it is a very familiar environment to write system software.
Rod Cope, take note. This is actually what God intended. This is, we actually, different God perhaps, but the Unix API is what God intended.
Exactly, and the key to the asynchronous model is that in the presence of long latency events, other events are not, that long latency does not bubble to other events that are unrelated. Obviously, you can still have situations where something takes a long time that causes a lot of other things to take a long time, but they're related things. They're not just like this thread was blocked for a long time and so couldn't do something else. And that's really critical.
Yeah, if that means nothing to you, by the way, you just haven't been a porn star in a particular variant of hardcore disaster porn that is the dog pile on a single slow disk, a single bad database that corks up entirely unrelated functionality in the ecosystem through a nest of dependencies that no one actually understood because no one actually understood how the system worked, a la Ben's keynote this morning. So it's very important. That orthogonality that you get with a pure event-driven system we found to be very important.
Right. So why did we pick Node.js in the first place? So as Brian alluded to, we spent a long time working on these systems developed in C. And to summarize, the event-oriented model sounds pretty interesting, right? It's like maybe there's another way to do this that might make our lives easier. You can certainly do that in C, but it's even easier to do that in Node. We talked about how Node isolates latency to the events that it actually would apply to as opposed to propagating that across the system. The important thing for us, remember, the whole point of this is to visualize performance in real time. So essentially, we're minimizing the time, the latency, between an event happening on some customer's compute node to them seeing it in the web browser, saying, OK, that's the spike that I just saw. So it's very important that we're able to deliver the data through the system in real time, and that's what Node is perfect for. Obviously, the fact that we're programming in JavaScript instead of C means that we can also iterate a lot faster in terms of just the development. We did have some reservations initially around things like observability. I had particular reservations around observability.
Just talk about it. I told you, just like come out and say it. It's fine. It's cool.
I think you shared some of these reservations. Is that wrong?
No, well, yeah, let's not rewrite history now.
All right, fair enough.
Dave had
some reservations.
Dave had some reservations.
We have a lot of tools in the operating system around understanding native programs. We have like pstack shows you a stack trace of the program. dtrace works in terms of functions. Our modular debugger has various programmable commands that show you things in terms of C functions. So when you're running JavaScript, it's just mangled C++ functions. So even if you understood the C++, which you don't because it's in JavaScript, or excuse me, because it's mangled, they're actually not what you want because you want the JavaScript. So observability is kind of a problem. And also the lack of post-mortem debugging, which is a particular sticking point for me. When a program crashes in most dynamic languages, all you get is a stack trace. And that's
did you self-medicate? Remember we talked about you can't talk about post-mortem debugging with Node without self-medication?
Yeah,
okay, that's good.
I'm almost at.
That's good. Cue in the water.
A stack trace is fine when you just had an undefined variable because you forgot to initialize this variable in this case. It's not really fine when you have an undefined class instance variable because it was supposed to have been set by an operation which must have happened before this operation. In other words, as you get a lot of concurrent things going on, the state interactions between those can be really complicated, and a stack trace doesn't tell you why that went wrong. What you need is a more sophisticated facility for that.
And as Dave's alluding to, our experience is all in kernel development. We are, for us, this was not a Node.js versus, I don't know, twisted Python or whatever discussion. This is a Node.js versus C. That was the only other alternative we would have considered. For us, coming from C-based systems that absolutely must be reliable, post-mortem debugging is absolutely essential, and that's what Dave and I are accustomed to, is that when the kernel pops, when a daemon pops, you actually have a crash dump or a core dump that you can go in and actually reason from and debug the problem. So that was a huge reason not to use Node, but all these other things we felt or I felt anyway.
Yes. Well, at the very least, we knew it was a good choice for a prototype, and if it didn't work, we wanted to know why it wasn't going to work.
Which is how I talked Dave into it.
That is how Brian talked me into it. The next major technology that we picked was Amqp. How many people here have deployed Amqp in production? OK, so a good number. Amqp is message queuing protocol. It's standard protocol for
Don't you want to ask the AMQP 0.9.1 versus AMQP 1.0?
So who's
the
deploying,
holy war between
who's deploying 1.0 of AMQP?
I would love, maybe someone after the talk, you can give us the backstory on the civil war in AMQP. I've never seen a standard completely revoke itself from one standard. Anyway, well, moving right along.
Right. So the obvious reason to use messaging is decouple the system components. We use AMQP because it's a standard one. We use RabbitMQ because it was already being used at Joyent, and it does have this reputation of reliability and performance.
Cue backpackers heading out on trail. I loved Ben's visual from this morning of the, everyone's heading out on the trail and just kind of their flip-flops and shorts, meanwhile, storm clouds on horizon.
So another question related to this, for those deploying AMQP in production, how many are using Rabbit? How many people are using something else?
What are you using? Cupid? What are you using?
ActiveMQ?
Yeah, interesting.
Cool. The reason why you wouldn't use AMQP for us, the only thing is you're funneling all this data through a single broker. So you potentially have an availability problem, which we weren't that concerned about. You potentially have a performance problem, but we wanted to quantify that before we chose a more complex architecture. So we basically just wanted to try it out. The next obvious one is the protocol that we use between the client and the server, and that's HTTP JSON. I don't think it really even merits much explaining.
Is this HTTP thing going to catch on? Is that what you're saying?
Yeah, I think so. I think so.
It's got legs. OK.
So
we'll see.
The bigger question for us is why not WebSockets? So a lot of times we talk about this, and people are like, oh, did you consider WebSockets for this? You're doing real-time stuff. You're streaming data from the server. Like, why wouldn't you use WebSockets? And the answer from us is usually, well, why actually would we use WebSockets? So the usual answer for that is, well, polling is inefficient, right? You're building a game. You don't know when events are going to happen. You don't want to poll every second or every 100 milliseconds. There's a lot of overhead associated with that. There's the overhead of creating a TCP connection, of processing the HTTP headers, and of actually just making a request and making the server do work when it doesn't need to. In our case, though, what we actually have is essentially a continuous data stream, right? You're constantly doing, again, to use the same example, you're doing a bunch of node HTTP requests, and we're just counting that. And we're essentially bucketizing it into 1-second intervals so that we can present it to you and show you what time it happened. But that discretization is pretty arbitrary. We're bucketing it into 1-second intervals. So for us, the fact that we're polling every second and saying what's the new data for this second is not really a waste. We know we need more data every second. So the only real overhead there, well, the other piece here is that you can eliminate the TCP connection overhead by just using keep alive. So the only real extra overhead here is the HTTP header the HTTP header processing, which we basically don't think would be a problem.
I think we were going to be elated to have that problem.
Yes,
to have,
exactly.
Like, boy, the only problem with this facility
problem
is that Nehalem can't process the HTTP headers fast enough.
Exactly.
Wow, that's a great problem to have, and we thought that we'd be kicking ass if that were our problem. If you look at what this saves you, and it introduces complexity. We actually like the fact that HTTP is standard protocol. You're not actually running a protocol within a protocol. So, and WebSockets is great. It's just that there's been this reaction to WebSockets to simply adopt it without questioning it, and we wanted to gather the data first and know that it was a problem before we adopted it.
Right, and the other thing for us is that we also support historical analytics. So you might say, what were the number of HTTP requests 10 minutes ago or 3 days ago? And it's sort of unclear how that even makes sense in the WebSocket model. Whereas if you just have an HTTP API that's like, here's the time, give me the data, it just works. So it just made a lot more sense for this abstraction. And then the last major component decision was why dtrace. It's not really much of a decision.
Wait, were you considering system tap?
I was thinking about doing this on system
tap. What the hell? What the hell, Dave?
What can I say? It turns out there's actually not really anything else that does all the things on this slide. So the key bits here are it's a comprehensive tracing framework for both the kernel and userland. It's suitable for production systems because it's absolutely safe. It has minimal overheads, you're disabled probe effect, blah, 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 right? The one really important aspect is it scales arbitrarily with the number of events that you're tracing. So again, to use the example of HTTP requests, we're not keeping an amount of data proportional to the number of HTTP requests you're doing. We actually, when you ask for this information, we basically go patch all the running node processes on the system to execute a small bit of code when you actually process an HTTP request, and we bump a counter. And then every second, we basically retrieve the value of that counter. So you can be doing hundreds of thousands of these on the system, and there's very little overhead from dtrace to do that. So that's really important.
I think another kind of important thing that dtrace buys us, especially with respect to OS-level virtualization. So those of you who aren't familiar with our model, we support both hardware-level virtualization and OS-level virtualization, where you have a virtual operating system, single OS kernel. With that OS-level virtualization, dtrace can see all the way up in there. So that's how we're able to get to these things, like looking at Node.js, for example, looking at MySQL, looking way up the stack, because we don't actually have a virtual machine sitting between the kernel and what's running. We support virtual machines too, but we're obviously more limited there in terms of what we can go do.
The last major design decision I want to talk about is around how we actually render the data, because this was something that was less trivial than we expected. So for standard, for simple data sets that are just like a line graph, it's pretty straightforward. You collect this data, the client requests the data, the client plots a line graph using one of many libraries. For drawing heat maps, like we were showing earlier, which was kind of obviously a really important feature that we wanted to get to, it's not clear that it's so simple, right? We talked about how it's actually a 4-dimensional data set. You have x-axis, y-axis, a number at each time, and then you have a number of, that's essentially a 3-dimensional heat map, and then you have one of those for each of the different things that you're interested in. So the number of different database tables you may have, for example. That's a lot of data, and it's a lot of data to be shipping back and forth every second. So when we were thinking about it, we were like, well, how would we like transmit that data? Actually, the most compact representation of that data is the heat map. So why don't we just generate the heat map on the server and then send it back? And so that's what we've done. And the worry there, obviously, would be that Node's strong suit is not exactly doing a lot of compute. And this is basically just raw compute, just generating this heat map. And the UI interaction would be a little bit more difficult because you basically have to pass parameters saying, you know, I want to color this bucket or this data stream or whatever it is. But that's what we went ahead and did.
And the actual times for that, by the way, I mean, it takes on the order of 7 milliseconds to render one of these pings server side. So the actual time is we strong believers, if you haven't already figured this out, just go measure something. If you actually think it may be too long, go measure it. And then you know it's too long if it's too long. There's too much fear. We're too fear-driven, and we kind of do things because, oh, surely this other way is too slow. Well, actually, these CPUs are fast. If you can ever get your problem CPU-bound, you're actually in pretty good shape. And so what we discovered is it just wasn't that big of a deal. I mean, we would have gone a different route had that not been acceptable, but it was more than acceptable. The other thing I would say is just in general, when you want to go visualize your data, developing your own infrastructure to go do that is not that hard. Please stop using RRD. The RRD tool is, I mean, has something so broken cast such a long shadow in IT. I mean, we can please stop using RRD. What it does is not that sophisticated. What it does do is broken. Write your own. It's not that hard. It really is not that hard. I mean, many of us have computer science degrees. This was a sophomore level programming project. You'll do it in like a week. And by the way, it'll be a week that you won't yell at your kids because you'll be happy. You'll be doing a nice little programming problem. It's fun. Maybe I'm the only one that yells at my kids when I'm having problems with software, but I don't think so. I actually think that I feel sorry for those of you. I mean, during that AWS outage.
That's what his kids tell me all the time whenever I see that.
How many kids were beaten within an inch of their life during the AWS outage? That's what I want to know. I mean, you got to figure that it was, I mean, that's the elephant in the room, people. It's the child abuse from our competitors. Oh, no, wait a minute. Oh, no, I'm sorry. Too far. Child abuse, not funny. Yeah, I get it. It's not funny. Okay.
All right, moving on.
I think we should move on. Let's move on to production experiences.
Moving right along. So now we want to talk about the problems we ran into with the technologies we chose and some of the problems we didn't expect to see based on those technologies. So first we're going to talk about the Node ones. The first thing is, well, we needed a bunch of C++ add-ons in Node to interact with dtrace, kstat, which is another Solaris data facility, and libping to actually generate the heat maps. How many people here have written an add-on in Node?
Yeah, Paul, that was actually a test to see if Paul had drifted off, or if Paul was still awake.
It's not really the streamlined path.
It's not the streamlined path. Yes, that's putting it very euphemistically.
So,
you know, Dave is known around the office as the public defender because there's no technology that Dave doesn't try to see the other side of. No matter how bad a technology is, Dave. So you know when the public defender won't take the case that it's a pretty extreme technology.
It's a bad sign.
It's a bad sign.
So one of the challenges you run into with these add-ons is that C++ has no stable binary interface. So if you compile Node with one compiler and compile your add-on with a different one, or even a different version of the same compiler, you load that thing up and it segfaults at runtime with some incredibly arcane error.
Did you bring my medication? Now I'm getting concerned about my medication.
I'm just saying. This is what happens. So we were able to work around this by, we basically just build everything together and we ship it together, but it's a huge pain in the ass. The other piece of this is using WAF to actually build the modules. I don't know if it's that people just don't deploy it well, or if it's a problem with WAF. I haven't actually dug into it.
Right, for the record, will the public defender take WAF's case?
No, but I don't know enough
Okay,
about
that's what
Exactly,
WAF should be more aptly named WTF, not WAF. What the hell? Why do we need another one of these? If you haven't used WAF, if you haven't known the WAF pain, this means nothing to you. But I just don't know. It's very well documented. That's the other thing I have to say. For something that is so disgusting and filthy, it's amazingly well documented. It's crazy. It's like, here's a map of my pubic region, hair by hair. It's like, dude, I can't unsee that. Like, why are you documenting this so thoroughly and not telling me what the fuck I'm looking at and why? Anyway, I'm sorry.
You did not bring your medication.
I did not bring my
obviously
medication.
Did not.
Damn it, I'm sorry. I'm sorry.
Okay. To give you an example of the kind of problem we've run into a surprising number of times, it's actually the same problem several times, is the node ping add-on looks for headers and the library in specific places, and if it can't find the library at build time, it just builds a node module that doesn't have a link to that library. And then you load it at runtime, and the thing crashes because it's like, I didn't find the symbol like ping create struct or whatever it is. And we've run into this several times because every time we change build environments, libping is in a different place, and we build the whole thing and start running it, and all of a sudden it just like crashes, like the heat map just disappears. And that's been very frustrating. and it's important to know, though, we've basically been able to work around all of these problems, but they've just been frustrating, basically. We talked a little bit about the limits we can run into with Node. For a while, we were concerned about the size of the Node heap, which we believe was limited at like 1.7 gigs. We haven't come anywhere near that problem, so that's been fine. The other issue is that the aggregator load could be limited by how much work you can do on one CPU. Although the actual ping generation for a heat map is something like 7 milliseconds, when you take into account the time we spend processing the HTTP requests and gathering the data up that we need to ship off to build this ping, it's more like 50 milliseconds. So there's a finite bound on how many of those things you can do on a single node process. But it turned out it was pretty easy for us to parallelize this. Remember, I spoke earlier about the way the flow works when you ask for a new piece of data. You're like, I'm interested in Node HTTP operations. We assign that to a particular aggregator, and then we just have a bunch of these aggregators. We have n CPUs of them, so that we know that we can just exhaust the box's resources if we have that much work.
And we've got nowhere near that problem. And we were petrified. Before we originally stood this up in production, we just didn't know what kind of load we were going to see. And even though we'd modeled it out, we thought that this wouldn't be a problem. I mean, we were talking about, like, OK, what if we end up totally tapped out on CPU? We'll bring in another node, and we'll start using CPUs on another compute node. But we just never.
Yeah, we haven't come close to that.
We haven't come close to it. Like, we just can't get this thing to consume much CPU at all.
Right.
Despite heavy use.
Yes, exactly. We talked a little bit about the observability problem. We had several solutions for this. We basically just wrote a bunch of tools to help out with that. We have this tool called CA Cuddle. I think Brian really appreciates.
I love Cactal.
Cactal. This uses Amqp to talk to all of the different services. So in our largest deployment, we've got like something like 70 or 80 distinct components of the CA distributed system. And this thing will go talk to all of them and then summarize the state of all of them and tell you if it's inconsistent or something like that. So that's pretty helpful. And it basically can show us all the internal state of those systems. We have Amqp Snoop, which basically is just, it's a like 100-line node program that just dumps out the Json payloads for all the Amqp messages flying by, which is a lot easier than using Snoop and Wireshark, which we also had to use sometimes. And Node Panic is the add-on that I was alluding to earlier that we created, so that basically when a node program crashes, instead of just getting a stack trace, you get a core file essentially of all of that program state. Now, all is a little bit misleading. It's actually whatever state that program was able to save ahead of time. So it's a lot of it, and it's been incredibly useful for us. But it's not everything, and we'll talk about that in a second.
Right, okay, yeah, it's not enough. One kind of cultural point here, these are all things that we implemented because as we stood this up in production, we shipped this as a software product, we also stood up in production. As we stood up in production, Dave and I and Robert Mustaki and the other folks at Joyent were on the production machines trying to understand what was going on with the facility, and not just debugging problems that existed, but actually watching the thing live in production. So to Mark, wherever Mark and Braccio is, but there you are, Mark. To your point about having that developer engagement with the software engineer engagement with production systems, I think that engagement, we've always believed in that engagement, but now we have got that engagement is much nearer for us because there's not a customer wall there. And for us, it's been incredibly valuable. I mean, a lot of this stuff came out of that. And you get a great deal of empathy for these production problems.
Yep. And so
too much empathy at times.
So we'll talk about one of the more interesting ones we had at first. When we first deployed on node.de at the very beginning of March, late February, one of the first things we ran into within was 12 hours or something like that. So it was very fast.
Right. Wasn't it before? It was before we deployed, I thought.
It was while we were on those systems, but I don't think we'd launched it yet.
Yeah, we hadn't launched yet. Right, because we had the bet about
Yes, exactly.
Right.
So within very shortly after deploying, within hours, we found an aggregator that was just spinning. It was not doing any system calls. It was not responding over AMQP or HTTP. When we used pstack on it, we saw it was running JavaScript. It appeared to basically be in an infinite loop in JavaScript. It was never even coming back to the event loop.
And this, by the way, is the advantage. So at Joyent, Ryan Dahl, the inventor of Node.js, works for Joyent. And the advantage of, we take Mark's kind of approach to the extreme. When we can't figure out what the hell is going on inside of Node.js, Ryan, get in here. And you kind of sit Ryan down, and Ryan can also feel the same pain. I think when Ryan would say that it's been very productive to, well, he might not use those exact words. He would use those words. If incentivized appropriately, he would use those words. If it was in his short-term interest, as Ben says. But it's been very productive for us to be able to sit down. And so a lot of the techniques that we used in collaboration with Ryan and figuring out, because we're really on the kind of the forefront, the leading edge of node deployment here.
And one of the interesting things for me about this is from this we realized we needed a way to be able to trigger a crash of that program using our panic facility that would save state over AMQP. But even that actually wouldn't have helped us in this case because it wasn't going back to the event loop. And similarly, Node had a facility for starting the debugger agent, which also required coming back to the event loop, which also didn't work. So it turns out we actually were never able to figure out what this was. We've never actually seen it again.
The ending here is terrible. This is an awful ending.
We've built tools and we've tested them in synthetic cases to actually be able to solve this kind of problem in the future, but we haven't actually seen it again.
And this is why the post-mortem debugging is so critical, because it is, it's emasculating for us to be up here and say that we don't know what the hell this was, and we just never saw it again. What's that? It's a six stop. No, a six stop.
No,
we're going to figure it out.
Stuff.
No, it was not a six stop. A six stop. No, you got to come downtown to go through a six stop. These race will find that. No. This was we were off in JavaScript la la land and not GCing and not doing a bunch of things compute bound in our code and no idea why. So we got to get that post-mortem debugging to figure or the USEC action.
And one of the more interesting results of this that we did was. So Ryan changed the SIG user 1 behavior to open up the debugger port immediately. And then we wrote a tool which basically sends it SIG user 1 and then uses our own post-mortem facility. Basically, you can use the debugger interface to invoke an arbitrary function. So we just invoke the function that dumps all of its state out, so you end up getting a stack trace that's like code where you're spinning in an infinite loop, like some stack frames in the debugger, and then like the code that you called to actually cause it to crash. So you can actually see exactly where it was, which is kind of cool.
It is very cool. Unfortunately, when you drop the SIG user 1 on it, it just opens up. It has got a hardwired port, effectively, and it will start listening onto that port. And actually, this is just recently we saw a problem unrelated to cloud analytics, but a node problem in production. And I fat-fingered it, and I dropped a SIG user 1 on every node process running on the box, as opposed to the one that I was interested in. So they're all like, oh, OK, I'll open up the debugger. And so, of course, only one of them succeeds, and the rest of them are like, well, I can't open up the debugger, so they're doing work. They're not dying. But then it's like, if you get this guy to restart, like, OK, restart you, then someone else attaches to the debugger. It's like, and it was a sad story. That was 100% pilot error.
It was a sad day.
Anyway, very mad at myself for that. It'd be nice to actually have a port there, to have a port specified. Anyway.
Here's another, unrelated to the previous problem, another node-related problem that we ran into. It's really the confluence of a bunch of things. But basically, when you ask for something like, I'll use a different example, like MySQL operations by latency or something like that, dtrace has to go instrument all the MySQL binaries on that system, all the processes on that system. And that takes a little while on a loaded system. It could take a couple of seconds. And for us, that's a synchronous operation. Just we hadn't done the work to make that asynchronous. We hoped it wasn't actually going to be that bad. And it turns out that can actually take a few seconds, during which the instrumenter is unable to report data for any other instrumentations. So you create an instrumentation, all of your other data potentially goes blank for a second or two, which kind of sucks. We basically need to make that asynchronous using EIO custom. And there are some complications around that with constraints on YAC, which is used by dtrace to compile the script. It's all very arcane. But.
Well, it's something you're very wary of with Node is that when you're doing an add-on and you are talking to a system service as part of that add-on, the Node is all asynchronous. So if you do something there that's, I mean, obviously you're doing synchronous things there with a kind of gentleman's agreement that they're not going to take very long. But if you do something that does have a latency bubble, like a dtrace enabling, you will cork the entire system very quickly. I mean, Node very much relies on the fact that everything is async. So you need to be careful when you're developing an add-on about it, and we need to go in, and this is not that hard to go do, but as I recall, there's some libdtrace bugs I need to go fix.
Constraints.
Constraints. Oh, thank you. Oh, God, that's so. Thank you, Public Defender.
So
Public Defender works for me.
Exactly. Public Defender works for everyone.
That's right. It works for the people.
So we talked about all these problems we had with Node. You might think it didn't work out that well, but actually, overall, we've really enjoyed it. We were just talking about these problems. The development was fast. We had a prototype up. I put down 2 weeks here, but it was really a lot faster when we actually had something reporting data from multiple systems, which is pretty cool. We were in production in 4 months. The prototype has evolved significantly since then, but it was never thrown out. We never reached the point where it was like, OK, we need to start again. So that was pretty big.
It never even really contemplated, I mean, changing the path we were on. I mean, it was not, because I think we know, too, that we've seen so many advantages of being event-oriented, and implementing that in C is just a nightmare.
Yeah. So CPU and memory usage have not been a problem, with the exception of the things we already talked about. Events. So remember, the whole point of this thing was we want to get data from when an event happens on a compute node to the browser as soon as possible. And generally, that happens within a few seconds. We actually wait an extra second or two anyway, because we basically, an event happens, you send data the following second, and then we wait up to a second for all those things to report. So we're about 2 or 3 seconds behind, but that's actually just because we want to wait long enough that we have all the data. It's been totally fine in terms of the latency of the whole system. And the tools that we've built and that already exist have given us adequate visibility. I wouldn't say it's amazing, but where they haven't been adequate, we've gone and created more tools. So there we go.
But more needs to be done there. That is we think the most active area, or should be the most active area for future node development.
Absolutely. I want to talk a little bit about some of the AMQP-related problems. One of them is related to exclusive queues. So the way the AMQP model works is typically each component has its own queue. It says, I'm interested in messages that look like this. That's called a binding. And you can say that the consumer of this queue is exclusive, which means only one person can be pulling messages off this queue. This makes it so that you can't accidentally have multiple services pretending to be the same guy, which could cause all kinds of mayhem as you drop every other message or something like that. But the problem is, well, OK, so you've set up this association. What happens when that consumer crashes? How does Rabbit find out about that? If the consumer crashes, your node program crashes, the kernel will close that socket. You'll close the TCP connection, and Rabbit will see that and say, like, OK, this guy's gone, so the lock on that queue is gone. What if the kernel actually panics, or you power off, or you have a hard reset? There's no way for Rabbit to know that, or the message broker more generally, right? You've got this TCP connection. This guy disappears. This guy will never find out until he tries to send another message and gets a reset. One possible solution to this is AMQP heartbeating, which is built into the protocol. We didn't use that because when this came up for us in production, we didn't have the client support for it, and it was a bigger risk to
Thank you, Theo. Thank you, Theo. Don't worry. You're gonna get the props. Yeah, Theo implemented this. I think this was the one example where the immaturity of the Node ecosystem hurt us.
Yes, that's probably true.
In general, everything we needed, we found, including the ping generation. There was a Node ping library, which worked well. This was the one example, AMQP heartbeating. There was Node AMQP, but Theo had not yet declared it put it under the Omni TI flag. And so now that's there, and we're going to go revisit that as soon as we've got the guts to do so.
Exactly. The solution we ended up going with is actually incredibly simple, which was basically when the consumer sees this error, it actually just sends a message to the guy who's supposedly him through the broker. And the broker will have to try and deliver that message to that guy. Now, if he actually exists, then you actually run into this problem and the consumer just blows up. But there's an actual problem there, so that's fine. If it's actually just a stale connection, the sending of that message and the corresponding reset will cause Rabbit to realize that this is gone, and then when you retry, it'll just work. So,
that worked good enough.
Yes, it was definitely good enough. And the important point here is that although this is an AMQP-specific problem, if you weren't using AMQP, you'd have the other problem, which is potentially misconfiguration causing multiple components to be acting as the same guy, which would be probably worse. Definitely worse, given how easy this was to work around. Another related problem we've had to deal with is around connectivity to the AMQP broker. And this actually has nothing to do with AMQP. This is just regular old TCP connections. Obviously, you can get disconnected at any time. Network failure, either guy crashes, something in the middle crashes. Even configuration change, as we saw when we went to production, we had a bunch of problems around that. Just changing the configuration of this thing can cause the network to be disrupted. There are several facets to this problem, right? First, the components have to be able to handle this. In Node, you sort of expect that you're going to get a close event on this socket before, say, a write will fail. But that's actually not true, because you can do a write, and the kernel has figured out already that this socket has been closed by the other side, and so the write returns epipe. So Node actually throws an exception. It may be that Node actually did already detect that the socket had closed and enqueued a close event, but you're actually running JavaScript at the time, so you can't handle that yet. Then you go do the write, and you get an exception thrown. And there are about 3 or 4 different ways in which that can actually manifest itself. And Node panic was actually crucial for understanding that state, because we were dumping the socket state, and so we were able to see, oh, this thing was actually explicitly closed by something. And then we could figure out which code path it was. The other thing is you have to be able to detect this case when it's idle, for the same problem we were describing before. If RabbitMQ crashes while an instrumenter is not actually doing anything, the instrumenter would never actually find out, because it's on a different system. It's not sending any data. It would have no way of knowing that connection was gone. So we solved that. That's another thing that could have been solved with heartbeating. And what we did for the same reasons, we just periodically ping ourselves, and we know that that will eventually cause this connection reset to be detected. And finally, this is actually kind of a node-specific problem. It's really an asynchronous model problem. What do you do actually while you're disconnected? In a lot of cases, you can flow control. You can say, OK, I want to stop my input source. But in our case, well, we have this constant stream of input. We can drop that data, and that's fine. That's one possible answer to the question. But it's kind of better if we don't, because what can happen is RabbitMQ crashes, but all of our components are up fine. And so if we just buffer that data for 10 seconds on the instrumenter, then we can send all that data to the aggregator, and we don't have any missing data, which would actually be pretty nice. Right now, we don't really handle this very well. We buffer the data indefinitely, and if the broker's down for a long time, then we crash because we run out of memory, which sucks. We need a sort of smarter policy around that. And all of these are problems with direct connections as well. Now, here's the interesting one.
Yeah, now so far this has been like Sports Illustrated swimsuit issue, and now it's time to get out the Victoria's Secret catalog, I think. Get into some serious hardcore soft porn.
Right. So about 2 weeks ago, we deployed Cloud Analytics to the joint public cloud, and at first, not first large scale, but largest scale deployment. And shortly afterwards, so everything was going great. We're all like, oh, let's go look at Cloud Analytics. Let's look at disk I/O latency, MySQL,
yeah, it was awesome.
HTTP.
Oh, God, it was
let's
awesome.
Look at everything. And it was great for about 10 minutes. It was about 10 minutes?
There was a honeymoon period of 10 minutes, yeah.
Yeah. And then RabbitMQ lost its mind. What do I mean by that? Well, we found it was using over 90% CPU usage, which is a lot.
On a friggin' 16-core Nehalem.
Exactly.
That's
a lot of
16 cores
CPU.
in Nehalem, 90%.
That's
like,
a lot of
whoa,
work.
That's a lot of friggin' instructions, Erlang. You better, and memory shot through the roof. Memory's going crazy. This thing looks like memory's going straight up the arm with this thing.
Right,
it's
going
on a memory bender.
Like a megabyte a minute, but like indefinitely. It's never coming back down at all.
Right, and of course it's like you go, and this is like, I've said this before, but the smugness of Erlang is annoying when these components are working for you, but when these components drive off the rails and start fucking you, the smugness of Erlang becomes enraging. So you go to the the RabbitMQ FAQ. It's like, Q, what do I do if I have a performance problem? A, you should be running Rabbit on which there are no performance problems. Or it's like, oh, why don't you check your queues? I'm sure there's memory buildup in their queues. No, actually, it's a funny story about the queues. Nothing on them. Hey, that's funny. Oh, well, then obviously your load is too high. Well, that would be true if I were trying to send more than 400 messages per second or whatever it was. Yeah. We're sending this paltry load. And of course, by the way, it is now, I thought I was going to go to bed that night, then realized I'm traveling that morning. You have the moment where you realized, I'm not going to bed, actually. Like, the cab is coming in 45 minutes to take me to the airport. Like, I need to get showered. And I'm in the cab, like, we're debugging this at 5 in the morning. Mark, I had flashbacks to your description of, like, I had to tell people, like, everyone go get sleep. Like, we will do something stupid, I'm sure. And unfortunately, then we could not go reproduce this in development. I mean,
yes, we spent a long time. We threw much greater load at it in development, we thought. Turned out that the scaling factor we run into, by the way, at this point, without reading the slides, I'm betting some people in here already knew what this problem was. I'm guessing a bunch of other people have run into this at some time. But it was very surprising for us because we saw the message queues. They were all length 0. Where is this memory going, right? So we spent a long time trying to reproduce this, and eventually we realized the only difference between the production system and the development system is the production system has all these other components with all these other bindings on it. And
yeah, it's worth mentioning that we simulated the production environment, and we would have basically you have as many consumers, same message load we have in production environment. The only thing we were not simulating properly was the number of bindings.
Right. The bindings are the rules saying, I'm a component X, here's my queue, and here are the messages I'm interested in. Now with Amqp, we're using the default. The popular thing is a topic exchange, which is essentially a regular expression match, which is kind of, when we realized it was the number of bindings, it all of a sudden made sense. Turns out we had 4,000 bindings on production. We were doing about 1,000 messages per second, I think.
Both not big numbers when you have 16
Right.
cores in the Halem, I would like to point out.
Absolutely. But that's a lot of regular expression matches to be doing for every single message that comes in.
It's still not that many. It still doesn't make
true.
sense. Don't take this case. Don't take this case. Drop this case.
You're right. You're right.
Oh, thank you. To the chair.
Exactly. So we did end up reproducing this by creating 1,500 bindings on the topic exchange that were not being used by anything, no messages going to them or anything. Just the presence of those bindings caused the exact same behavior. And it turned out, in the newer version of the software, they've actually fixed this. They fixed this with fast topic routing.
Fast topic routing. Do you mean non-pathological topic routing? Because I'm
what
looking
I
for
said.
non-pathological topic routing.
Exactly.
I'm looking for topic routing that doesn't take 16 cores in a Halem to route 5. Anyway, yeah, baby.
Right. So that is, I wrote that as possible solution. We haven't actually tried that yet. What we did, which was very simple, was just use a direct exchange, which means you're basically just doing a string compare rather than a regular expression match. And that was like night and day as soon as we deployed that, down to like 8% CPU usage, 40 megabytes of DRAM, and doing the same load.
So, and I want to hop to a demo here. So, where are we on
Can I switch you?
Yeah. Do we want to hit the? So anyway, AMQP. We have the good parts of AMQP. The latency has been good enough. The bad part is when Erlang loses its mind, obviously. Anyway, summary is that the stuff basically worked. I mean,
yes.
The problems, we did have to kind of rack our brains to go make sure we're going through all the problems we had. Mm-hmm. But we want to actually demo this thing on a production system because I say demo on a production system or GTFO.
Ready for the switch?
Yeah, hold on just a second. Hold on. Yeah, no, not yet. No, exactly. I have to set up all the smoke and mirrors. OK, switch me over now.
Ready?
Yes. OK, so I am on the operator portal of our new deployment of a public cloud in one of our data centers. And what I'm going to do here, you can see these are all the instrumentations we can pick from. We've got a ton to pick from here. And some of these are, like MySQL and so on, MySQL queries are all up the stack in the virtual OS instance. Some of these things are in terms of lower in the stack, for example, disk I/O operations and so on. What I'm going to pick actually is, you see this virtual machine category. So people may have seen that we ported KVM to our Illumos variant called SmartOS. And so these are all running under KVM. And let's actually do virtual machine disk I/O operations. Let's do this broken down by, we'll do this decomposed by latency and server host name. Ooh, or zone name. Let's do zone name. What we're doing when I hit the create button, and I got to tell you that my heart, this is not good for me cardiacally. This is not good for my heart to actually go do this because what we've done, someone said earlier in Mark's talk that to automate is to actually distribute your failure. So what we have actually done is run dtrace on the entire cloud at once. Dtrace, of course, operates by dynamic instrumentation of running program text. So we've actually dynamically modified every running kernel in the joint cloud. We designed dtrace to be absolutely safe, and I've run dtrace lots and lots and lots in my life. But it's still true when I'm on a production system, like the heart rate goes up just a little bit. Yeah, don't look at the Ryan nervously. No one nervously look at the screen. That is not fair. That is not right. I'm just going to, and I'll explain here what we're seeing. But so what we have gone and we've done that across many, many machines. And like I said, it's not good for my heart to watch this. So what we're seeing is these are the actual zones themselves. These are kernel virtual machines. I don't know if Arthur's in the room, but he was actually hitting some I/O pretty hard recently. What we're seeing is latency up to 40 milliseconds. Not so bad, but we may want to understand that a little bit better. What I'm going to do is actually zoom in down to the, let's get down here. And we can see that most of this I/O, actually, So this is most of this I/O is within a millisecond. I could go and let's pause this.
Remember, these are virtual disks.
These are virtual disks, yes. And if I now click on this guy, I can actually see that's that additional level of dimensionality I was describing. So you can actually see how much of this I/O is coming from that particular zone. How much of the I/O is coming from this particular zone, and so on. Now, you can do this yourself as well as a user. What I'm showing you here is an operator's view. So this is the operator's view of the entire cloud. You can do this as a customer as well, or as one who's using the cloud, except that you're not going to see all the machines, sorry. You will see all of the virtual machines that you have, all of your virtual machines. So you'll be able to answer the question very quickly of, am I seeing an I/O latency problem? And the design center for this really for us is we want, when you have a production performance problem, unlike with a fatal failure, where it's very clear where it's coming from, when you have a production performance problem, and again, we believe that with the rise of dirty apps, we're going to see more of these, not fewer of them, fingers get pointed in all directions. Right? Everyone is pointing fingers at everyone else. The networking guys are pointing fingers at the storage guys. If you have got your own infrastructure, everyone's pointing a finger at you. If you're cloud-born, you're pointing a finger at Amazon kind of weekly. But you're trying to figure out, is it from the network? Is it from storage? Is it my app? Is it the infrastructure I'm running on? We want you to be able to answer those questions very quickly and be able to very quickly determine it's not this, it's not this, it's not this. Oh, okay, wait a minute. Looks like this could be a MySQL problem, or looks like this could be a Postgres problem. Looks like this is an I/O problem with my provider, and so on. So that's what we've really sought to do. And from the operator's perspective, we want an operator to be able to operate the cloud and give you a first-class service without you having to pick up the phone and complain. With that, I think we've got probably a very few, 3 minutes for questions. Any questions? Yes, Wes.
As a software vendor, is it possible for a software vendor to add metrics to show?
Yes, great question. So, Dave, do you want to talk about MetaD for a minute?
Sure. So one of the things that became clear early on was if you've used dtrace, you know that in order to actually generate this kind of data, you have to write a script in the D language. And in order for us to be able to do, say, something like virtual disk operations by all kinds of possible decompositions, it's actually a family of D scripts that corresponds to, and we had to be able to generate them automatically. So we have a essentially declarative way of expressing a family of D scripts like that. So for example, for VM disk operations, there's a JSON file that describes how to write that D script. And that allows us to add these new metrics by just dropping one of these new files in there. Now, we don't actually have the facility for sort of the nice API for someone to say, like, ship us one of these scripts and just have it immediately show up. But that's definitely on the roadmap, and it's most of the hard work is done there.
Yeah, technically it's very easy to go do. So if you've got your own software infrastructure and want to add your own probes to it and plug this in, we should talk, because it's not hard to do. The last time I told Wes something like that wasn't hard to do, he did it while I was speaking for the rest of the presentation. OSCON 2005. We'll always have OSCON, baby. We'll always have OSCON. Yes? Yeah, great question. So we keep some amount of persistence. What we decided to do is to fix the data that we will keep, but you can adjust the granularity. So we keep actually a relatively small number of data points, because we don't want to be in the business of storing all this data for you. What we have done is, so we store some of it for you, but most importantly, all this is available via API. So if you want to store this data and do something with it, that's awesome, and you should just consume it via the API. And indeed, the client that we're using uses the API. So we use all the APIs to build everything that we've got. The API really is that first principle, and you should take the data and do something cool with it, and just tell us what you do. That'd be great. But you can persist it yourself.
Well, but you're presenting.
Yeah. Yeah, so you can actually pull the raw data. So you're going to want to pull the raw data. You can take the heat maps if you want and store them somewhere. Don't know if that's going to be useful to you or not. But you can actually, you can just pull the raw. Actually, interesting, you're seeing some banding there. Of course, we're at the 1 millisecond level. You're probably seeing, that is almost certainly cache effects there, because this is now 1,000 microseconds. Anyway, yes? Yeah, so I mean, I would say that what we've offered right now is kind of the portal, I would say, is the tool we've offered to consume it. But if there are other tools you want, I mean, it's just an HTTP API. It's very well documented. Actually, we have a slide. I think we've got a slide that has the documentation on the API, right? No. Yes. It's not, but it would be easy to go do that. I mean, if you're interested in that stuff, definitely talk to us and we can figure something out. It's all there. It's all technically very possible. You bet. Absolutely. Great. Thank you so much.
Thanks a lot.